everyone. In this video, we're going to talk a little bit more about continuity and differentiability. Okay, so let's start by reviewing continuity before we get into differentiability. So remember, a function is continuous at a point if, and remember, you have to go through the three conditions of continuity, okay? I did want to show you that this is a little bit different way to write the same thing, okay? But in the past, we learned it like this. Number one, the function has to be defined at the point x equals c. Number two, the limit as x approaches c has to exist. And the most important, number three, they have to equal each other. Okay, so remember that in order for the limit to exist in step 2, your one-sided limits have to be equal to each other. So I like this statement here because it's a condensed version of the three tests of continuity. Okay, so this is just saying that the limit as x approaches c from the left of f of x equals f of c, which also equals the limit as x approaches c from the right of f of x. Okay, now you guys, this is not new, this is just review. We've answered questions like this before. Is the function continuous at x equals -2? To answer this question, you want to go through the three steps or tests of continuity, okay? So you just start with step 1. Find f of -2. So remember, when we're evaluating a function, we are trying to figure out what y equals when x equals -2. So based on our piecewise function, see here how x is greater than or equal to -2, we would plug in to the x squared plus 3x, and I'm just plugging in -2 for x in order to evaluate the function. Okay, so let's work it out. -2 squared is 4. 3 times -2 is -6, and then -2. Work it left to right. We'll have 4 minus 6, which is -2. -2 minus 2 is -4. All right, step 2, we have to evaluate the limit as x approaches -2. Now, based on this piecewise function, remember, in order for the two-sided limit to exist, your one-sided limits have to equal each other. Okay, so we're going to have to evaluate our one-sided limits. So let's start with x approaching -2 from the left. I always like to just start from the left. Well, remember, and if this is helpful, you guys, you should write it out. Here's -2 on our number line. If x is approaching -2 from the left, then these x values are less than -2. So we're actually going to plug into the -x squared. So we'll have negative, and then we'll have -2 squared. And you evaluate your exponent first. So -2 squared is 4, but then times -1 would give us -4. Okay? Evaluate the limit as x approaches -2 from the right. So again, we're approaching -2 from the right, then these values of x are greater than -2. So again, we're going to plug into that first piece, which we've already done, so we already know what it equals. It equals -4. Okay, so you guys, we could now establish that because all of these are equal, we know f of -2 equals the limit as x approaches -2 of f of x. Therefore, f of x is continuous at x equals -2. Okay, now let's talk about differentiability. So you guys remember we started our discussion about the derivative as slope of the tangent line. And remember, the first way you found a derivative was as a limit. Okay, so you probably recognize, hopefully, that these two limits represent definition of the derivative. Okay, so the idea here was that f of x minus f of c over x minus c, like this is how we would find slope of the secant line. But then to get slope of the tangent line, we would move the points together, so x would be approaching c. And we know in order for a two-sided limit to exist, your one-sided limits have to equal each other, okay? So this is saying a function is differentiable at x equals c if and only if the limit as x approaches c from the left of the slope of the secant line equals the limit as x approaches c from the right of the slopes of the secant lines, okay? Because remember, derivative is a limit, okay? So in order for the derivative to exist, those one-sided limits would have to equal each other, okay? All right, so let's look at the example. Notice again, we're given a piecewise function, and we're asked, is the function differentiable at x equals -1? Well, first of all, for the function to be differentiable at a point, the function has to be continuous at that point. Okay, so that's why I reviewed continuity, because to answer a question like this, I would always start by checking continuity. Because if the function is not continuous at the point, we know it's not differentiable at the point. Okay, because if it's not continuous, that means there's a discontinuity in the graph at that point. So remember, the derivative does not exist at a discontinuity. Okay, we've already talked about that in the past. All right, so anyway, I would start with continuity. So we're just going to go through our 3 tests of continuity. So we've got to evaluate the function at -1. So again, that's where I would look for where x is greater than or equal to -1. So I'm going to plug in here to evaluate the function. Okay, so -1 squared is 1. We'll end up with 1 minus 1 minus 3, which will equal -3. Okay, 2, we got to evaluate the limit. And we're going to have to evaluate our one-sided limits in order to evaluate the two-sided limit. So why don't we just start with from the left? I just like from the left first. But to evaluate the limit as x approaches -1 from the left, I'm actually going to plug into the -x minus 4, because this is where x is less than -1. So that'll be, we'll have the negative out front, but then I'm plugging in a -1 for x minus 4. This will end up equaling 1 minus 4, which equals -3. Okay, so far so good. Let's check the limit as x approaches -1 from the right. Well, again, from the right, that means x is greater than -1. I'm going to plug into the x squared plus x minus 3, but you know, we've already done that, so we already know what that equals. Okay, so number 3, we can say f of -1 equals the limit as x approaches -1. Notice this is my two-sided limit now. Okay, which I know equals -3 based on the one-sided limits. Okay, so therefore we know f of x is continuous at x equals -1. All right, so since the continuity checked out, we're now going to have to test differentiability. Okay, so to check the differentiability, okay, so you guys, we do have to, like, don't forget that a derivative actually is a limit. So we are, in a way, making sure that the two-sided limits are the same, because for the general, we're trying to make sure the one-sided limits are the same, because that would have to be true for the two-sided limit to exist. But, you guys, we're not going to go back to the old way. Like, these stand for the derivative, okay? So we really just need to make sure that the derivative of the function, the limit as x approaches c from the left of f prime equals the limit as x approaches c from the right of f prime. Like, we just need to make sure that the derivatives are the same from both directions, okay? Because remember, the derivative is the limit, okay? So all I'm going to do is I'm going to find the derivative of each piece. So if I find the derivative of x squared plus x minus 3, that'll be 2x plus 1 when x is greater than or equal to negative 1. And you know what? We can even call this is f prime of x. You're just deriving each piece. The derivative of negative x minus 4 is just negative 1. So when I find the limit as x approaches negative 1 from the left of the 2x plus 1, which means I'm going to plug in negative 1, that's going to give me negative 2 plus 1, which equals negative 1. And then if I evaluate the limit as x approaches negative 1 from the right, oh, actually, I'm sorry, I mixed those up. Let me go back. From the left would be the bottom function, because that's where x is less than. So that would be just finding the limit of a constant, which is the constant. And then the limit is x approaches negative 1 from the right, which is where x is greater than or equal to negative 1, is where I'm going to use the 2x plus 1. So again, plug in negative 1. So we'll get negative 2 plus 1, which equals negative 1. But check it out. Those limits are equal to each other. So we can say, yes, therefore, f of x is differentiable at x equals negative 1 as well. Okay. So you guys, that's how you would answer a question like this. Is the function differentiable at a point? You would check for continuity first. So that goes back to our definition of continuity that we learned in the first unit. And as long as the function is continuous, then you would carry on and check differentiability. But if you found that the function is not continuous, then we know that it's not differentiable, okay? But you guys, don't assume that because the function is continuous that it is also differentiable. Because remember, we learned that differentiability implies continuity, but not the other way around. Continuity does not imply differentiability because you could have a sharp corner in the graph. Absolute value function is an example, okay? The graph of absolute value of x is continuous, but it's not differentiable at the sharp corner, okay? All right, now let's look at an example like this where instead of being asked, is the function differentiable at a point, you are asked to find the values of a and b that make the function differentiable. Okay, so you guys, we're going to approach this the same way. We're going to, anytime you're solving for two unknowns, so like here we're solving for a and b, you know you have to set up a system of equations, okay, because that's the only way you're going to be able to solve for the two unknowns. So you're always going to set up two equations. Now, for these problems, you're going to set up one equation based on continuity, because in order for the function to be differentiable, it has to be continuous. And then we're going to set up a second equation based on differentiability, okay? All right, so let's do that. Okay, so my equation based on continuity, remember that's where I'm just going to plug in 1 for x, and I'm going to set the equations equal to each other. And again, that is based on the definition of continuity, okay? So if I plug in 1 for x, here I'll end up with a plus 1 equals, and then if I plug in 1 here, I'll end up with b minus 3. So we'll have a plus 1 equals b minus 3. Okay, then we're going to set up an equation based on differentiability. Okay, so we're going to find the derivative of this piecewise function, which again, that just means you'll derive each piece, okay? Now, when we find the derivative of ax squared, we're going to use power rule, but because we don't know what a is, we're just going to leave it there. So the derivative will just be 2 times a times x. And derivative of 1 is 0. And just keep the inequalities the same. Okay, the derivative of bx is going to be b, the coefficient, when x is less than 1. Okay, now we're going to do the same thing. We're going to plug in 1 for x and set the two pieces equal to each other. So I'll end up with 2 times a equals b. Okay, now I have two equations. I'm noticing, this equation is already solved for b. So I can just take the 2a and substitute it here in place of b. And I'll have a plus 1 equals 2 times a minus 3. Now I can just solve for a pretty easily. So I'm going to subtract 2a on both sides. We'll get negative a plus 1 equals negative 3. And I'm going to subtract 1, negative a equals negative 4. And then we could divide by negative 1 on each side, and we get a equals 4. Okay, now we know b equals 2 times a. So now we know that b is equal to 2 times 4, or 8. And there we have it. These are the values of a and b that make the function differentiable. Okay, so you set up one equation based on continuity, and then the second equation based on differentiability, where you're just finding the derivatives. And then you just solve the system of equations. All right, you guys, so we're going to stop there, and we'll definitely practice this some more in class tomorrow. But as always, thank you for watching, and have a good night.